Hello everybody. In this video, we tried to design a compensator in the frequency domain for the given system. As you can see again here, GP is equal to 10 divided by 1 plus s squared as the transfer function. If you remember, the requirements are to have steady state error smaller than 1% for the unity step input, cutoff frequency or crossover frequency bigger than 1 radian per second, phase margin bigger than 20 degrees, gamma n equal to 0.1 for frequencies bigger than 10 radian per second, and gamma d equal to again 0.1 for frequencies smaller than 0.1. In the last video we designed a lag compensator in the frequency domain, and then we justified that all the requirements are satisfied. But if you remember, right at the beginning of the example, we had shown that using a proportional controller, we were able to satisfy the steady state area. However, by setting the proportional controller's value to 1, by simply forming the unity feedback, we had seen that referring to the body plot of GP j omega, we had cutoff frequency bigger than 1 radian per second, phase margin bigger than 20 degrees, gamma n, the requirements on the attenuation of the noise was already satisfactory, and we only needed to increase the amplitude for low frequencies in order to have a better performance in terms of the steady state error, and also to satisfy the attenuation of the disturbance. Now in this video we are going to design a PI controller. So our compensator will be a PI1. Proportional integrative one, instead of using a lag compensator, yeah. And we will see how will be the performance of the closed loop system. And then you can see what are the differences and what are the similarities between the PI controller and the lag controller. And you should remember from the root locus analysis that PI controller and the lag controllers are kind of similar to each other. Both of them are used in order to increase the behavior of the system in terms of the rate error, let's say. On the other hand, we know that by adding the PI controller, we are increasing the type of the system. In this case, the type of our system will become equal to 1, and therefore the steady state error for the unity step input will become already equal to 0. We just need to check the other requirements for the cutoff frequency, for phase margin, for attenuation of the noise and attenuation of the disturbance to make sure that all the requirements are satisfied. So let's plot again the body plot that we had for our GP j omega. Here we have the amplitude in terms of omega, and here we have the angular phase. The corner frequency in our case for Gj omega is 1. Again, if you remember, the crossover frequency was equal to 3, omega is equal to 3. At 1 we had the amplitude equal to 20 dB. So here's 20 decibel. And at the frequency of 10 we had minus 20 decibel. For low frequencies, the amplitude graph was a flat line with 20 dB as the amplitude, and then for starting from the frequency of 1, we started to have this declining, the line with the slope of minus 40 dB per decade. For which at the frequency of 10 we had the amplitude equal to minus 20 dB. In terms of the phase or angle plot, the original phase that we had was 0 degrees, and at the frequency, at very high frequencies, as omega goes towards plus infinity, the phase becomes minus pi. So here we have minus pi over 2, 0. And if these are the asymptotic lines, so this is somehow the phase plot that we have for Gj omega. Alright, so for this system at the cutoff frequency omega is equal to 3, we can determine what's the value for the phase margin. It's equal to 36.9 degrees, which is already a satisfactory value. The cutoff frequency is 3 radian per second, which is again a satisfactory value according to the requirements. And we also can determine the dangerous areas for the noise and for attenuation of the noise and for attenuation of the disturbance. So this is the area in which our amplitude body plot shouldn't enter, otherwise the noise will not be attenuated by the given factor. And here is the area for the attenuation or for the rejection of the disturbance. So as you can see here, we could say that the behavior of the system for frequencies larger than, let's say, 1 radian per second is already a good one. Yeah, we have the cutoff frequency equal to 3, we have the phase margin equal to 36 degrees, and the attenuation of the noise is satisfactory. Okay, so what we need to do in this case is to modify the amplitude graph for low frequencies in order to obtain the requirement on the steady state error, and also to satisfy the rejection of the disturbance. And as I already mentioned, we are going to use a PI compensator. So for the PI compensator, GCS, we can, so you already know what's the transfer function for the compensator, yeah? So it can be written as Kp plus Ki over S, or in other terms, we can have K over S times S plus 1 over Ti, which determines that we have one pole at the origin and 1 0 at minus 1 over Ti, and this Ti is depends, the value of the Ti here depends on the value of Kp and Ki for sure. So we have a 0 for the compensator at minus 1 over Ti, and we have the pole of the compensator at the origin. If you remember, we already had drawn the Bode plot for this compensator, for the PI compensator. Amplitude, phase, for different values of the amplitude graph, and here we have the phase graph. The corner frequency is 1 Ti. for very low frequencies, the phase will be equal to minus pi or 2, and for the high frequencies, the phase will become 0. So here, if we have minus pi over 2, let's say that this is the asymptote, minus pi over 4. This will be the phase plot for the control, for the PI control. Regarding the amplitude, for very low frequencies, we will have a line for the amplitude with a slope of minus 20 dB per decade, and for very high frequencies, the amplitude will be equal to 20 logarithm k in the decibels, and at the frequency equal to 1 over pi, we will have a even value. Saying that we now draw the asymptotic amplitude graph, we will have a graph like this with minus 20 dB per decade for low frequencies, and with an amplitude at infinity, which is equal to 20 logarithm of k. So here k is the factor, or let's say is the kind of DC gain of the controller. Yeah. Okay, now let's see how we can manipulate the Bode plot of the overall system in order to obtain the required characteristics for the system. So as I already mentioned, we want to manipulate the low frequency behavior, and we want to keep the high frequency behavior similar to the original case. Yeah, on the other hand, so to do so, let's say, we have to place the zero of the controller at frequencies lower than the cutoff frequency, which was the cutoff frequency was 3. But in order to keep this kind of similar behavior for the high frequencies, we will place the zero moderate compensator at frequency equal to 0.1. So let's say if we place the zero of the controller at minus 0.1 and the pole at the origin, we will not affect the high frequency behavior of the system in this case. We will see when we draw the Bode plot of the overall system. So in this case, we will have with ZC equal to minus 0.1, we can obtain Ti equal to 10. And from here, we can obtain the GCS in terms of Kp and Ki. But on the other hand, keep in mind that since we don't want to affect the high frequency behavior, we need to have 20 logarithm of amplitude of the K, which is the amplitude for the high frequencies of the compensator, to be equal to 0 dB. So if we set this equal to 0 dB, from here we will get K equal to 1. This means that we need to have Kp equal to 1, and then accordingly we can determine the value for Ki. So we know that GCS is equal to Kp plus Ki over S, and since Kp is equal to 1, we have 1 plus Ki over S, or in other words, S over S plus Ki, and we to have the 0 of the controller at minus 0.1. So from here, the value for Ki can be determined as 0.1, and accordingly the GCS will be obtained as S plus 0.1 over S. Or in other terms, we can write GCS is equal to 0.1 times 1 plus 10s, or GC j omega is equal to 0.1 1 plus j 10 omega over j omega. Now if you draw the body plot for this GC j omega and then draw the body plot for GC omega times GP j omega, you will see that all the requirements are already satisfied. Again, draw the body plot for this compensator just to practice. Amplitude, and phase plot for GC j omega equal to j omega plus 0.1 over j omega. So the corner frequency here is 0.1. And here we will have the amplitude for the body plot is minus 20 dB at the beginning, and then 0 dB for high frequencies. Regarding the phase, we will start with minus pi over 2 and then gradually go towards 0 degrees. Now if we combine GC j omega with the GP j omega that we already had, we will obtain L j omega, which is our final transfer function for the loop. We have GC j omega times GP j omega. So for L, we will get 0.1 times, or we can directly write now LS. LS will be equal to 0.1 times 1 plus 10s over s, and this should be multiplied by the GP, the transfer function that we have for the plan, which is 10 over 1 plus s squared. Divide times 10 over 1 plus s squared. So our LS will be obtained as s times 1 plus s squared, and in the numerator we will have 1 plus 10s. Now we can draw the body plot for Lj omega and verify that all the requirements are satisfied. So we will have these frequencies as the corner frequencies, 0.1, 1, 10, or maybe let me use a better scaling. If here is 1, 0.1, 10, and same here, same frequencies. So for frequencies smaller than 0.1, we are going to add this minus 20 dB predicate, which comes from the controller, from the GCG omega, to this flat line which we had from the original process. So for very low frequencies, we will have the slope of the amplitude line equal to minus 20 dB per decade, which will be the case for the frequencies up to 0.1. Afterwards, after 0.1, since we are adding 0 dB to the amplitude, we will have exactly whatever we have here in this, let's say, section of the body plot for the GP. Right, so at omega equal to 0.1, we will have 20 dB. So accordingly, this will be our body plot. Here is 20 dB. So until here, until this frequency omega equal to 0.1, we will have the line. Then up to the frequency equal to 1, we will have the flat line with the amplitude of 20 decibels. And then afterwards, we will have the line with the amplitude of minus 40 dB per decade. The cutoff frequency again would be close to 2 radians per second. Regarding the phase, going back to what we have as the phase plot for the controller, you can see that for high frequencies, for frequencies higher than 1 radian per second, the contribution of the phase on the overall system is quite negligible. And for the low frequencies, we have significant contribution of the controller, starting from minus pi over 2 till 0. So this will be added with the phase plot that we have for the process itself, starting at 0 degree going to the frequency equal to minus 1. So adding these to each other, you can get this plot for the phase. So if this is minus pi over 2, minus pi over 4 and 0, and this is the phase plot for L. Here is 1, here is omega c. So you can also check the phase margin afterwards, after plotting this. You will get the correct value, let's say. I mean that the value which is already satisfactory. So we know that at very high frequencies, again we will have minus pi as the phase of the system. This will be roughly the phase that we can get, that we will get by combining the two phases here. Let me just double check. So we have minus pi over 2 at the beginning, and we have 0 minus pi over 2 for the compensator and 0 degree for the process itself. So if we combine them with each other, we will get minus pi over 2, yeah? So we should start from minus pi over 2, not from 0. Sorry for this. Okay. So starting from minus pi over 2, the phase will decrease, let's say. It will go up to around 45, minus 45 degrees, somewhere between 1, the frequency equal to 0.1 and 1, so we will have this kind of behavior, and then it will start to decrease and go towards minus pi. Yeah, maybe this is not the correct one. This might be more realistic. However, you can easily draw it with the MATLAB commands. Now we can determine what's the phase margin for the system. At this frequency, this will provide us the phase margin, which you can double check. The phase margin in this case is equal to 35 degrees, which is already a satisfactory value. The cutoff frequency is still omega c is equal to 3 radians per second. What's the steady state error? I believe you should know it right now. Yeah, do you need to calculate it? Let me know it as the feedback. And then regarding the attenuation of the noise and the rejection of the disturbance, we already know that these are the dangerous areas for the disturbance and for the noise. Yeah? And as you can see here, our body plot has not entered these areas. So all the requirements are satisfied using this using proportional, integrative, or PI compensate. Okay, thank you for your attention. Try to draw all the body plots using MATLAB and compare them with what we have here. Thank you for watching.